Okay. So in the quiz you just did, you have a force on an object, namely the planet. If the planet was right in the middle of between the two stars, then it would be in equilibrium. It would just sit there. But you perturb it a little bit in the y direction, and it'll oscillate up and down, up and down, up and down. And you can calculate, and hopefully most of you did that, calculate what the frequency of oscillation is. All right? So oscillations are everywhere. Whenever a system is in equilibrium and you perturb it away from equilibrium, you will get oscillations, almost always. Okay? And right now, there's all kinds of oscillations going on in your body. So for instance, you have a heartbeat. That's an oscillation. And that can be described in many ways using the kinds of analysis that we have been using. Your brain oscillates. You have brain waves. All right? And I'm going to talk, if I have time, a little bit at the end today about what the nature of some of those oscillations are like and why they are the way they are. Okay. So what we want to do today is go a little bit beyond simple harmonic oscillations. And we're going to use as our basic model a very simple pendulum. And I made a very, very simple one here. Okay, so this is a pendulum. It's just going back and forth, back and forth. All right? So we talked about this a little bit on Thursday. So I'm going to write down what the key ideas are from Thursday. So if you remember, we ended up with the following equation for a pendulum. We had the rate of change of the angle with respect to time. Imagine here's our pendulum here. We call this angle theta and this length L. All right. You end up with this is minus g over L times the sine of theta. And that's approximately, for small angle, GL theta for, let's say, theta much less than 1. Actually, it works pretty good even for theta near 1. Works pretty well. All right? But we're going to actually see what happens when theta is big. All right? And the solution to this is theta is equal to some amplitude times the cosine, let's say, of omega t, where omega is the square root of g over L. All right? So you can work this out. This comes from the equation torque equals I alpha. And then this solution comes from just putting this into this equation here. So you take two derivatives. You put the second derivative in there. You put the theta itself there. And you'll see that it works. OK? All right? That's how you get your frequency omega. Now, we're going to need one other quantity, d theta dt. And that's going to equal theta 0 omega times the sine omega t. And there's a minus sign there. OK? So you have how the angle changes and how the rate of change of the angle changes. So notice that if I plotted this versus this, I think we talked about this in a number of contexts, you will get an ellipse. All right? So let's see how that actually shows up on a computer simulation of this. So I have a little simulation here. So I'm starting out the system with theta equals theta 0, some value, 0.4. There's no angular velocity, so I'm going to stick that in as 0. Right, then I'm going to initialize the thing. And then I'm going to run it. All right, so I'm going to run it. So there you see what happens. All right, so you get nice oscillations. They look pretty sinusoidal. All right, and this is a plot of the angular velocity, or yeah, the angular velocity versus the angle itself. And notice you get an ellipse. All right, this other little plot over here, we'll need this later, plots the same thing as this, but only every pi seconds. And we do that for a particular reason. It's not relevant here, but later it will be. You can think of this like do you know what a strobe light is? Strobe light, flashing lights that might see if you ever went dancing or something, right? You know what that is? Okay. Watch some more American movies and look at whenever there's dancing going on, frequently there's some kind of flashing light that goes on and off, on and off. Right? That's called a strobe light. So what we're doing here in this plot is we're just plotting a point every so often. All right? And we'll use that later. All right. So now we have this situation here. Now the first thing that we can add to simple harmonic motion, which is always going to be there, is damping. Now what do we mean by damping? What we mean is there's some usually fluid friction that slows down the oscillations. And the question is, what is that going to do to the oscillations? All right, so our new equation now looks like this. All right, so here is our damping, and it's proportional to the speed at which the pendulum is moving. All right, and then we have what we had before, but I'm going to put it in right away as the omega squared, as omega 0 squared times theta. So this is just G over L. Okay? So it's the same thing as this equation right here, exactly the same, except I'm going to add in some damping. All right, let's see if you're thinking. Let me show you a little bit physically what's happening. Here's a pendulum. So if I let it go, what do you think is going to happen? Anyone notice anything? Is it changing at all? What's happening? Slows down, the angle gets smaller. That's what you see. What do you think you would see on this plot? What should happen? It's going to get smaller and smaller. What do you think is going to happen to this guy? What is going to happen in this plot here? So here it started. So there's a certain value of theta. Notice the angular velocity is up here, is 0. So it started out at 0, but then it speeded up a little bit, but it went around and around and circled in here. And then on the time graph, the oscillation amplitude decreases with time. All right? Now what's going on over here? We're right in the center. Let's see if we can see what's going on. Notice the size of the axis up here, 20, 30, minus 30, 25, 35. Similarly here. Just keep that in mind. All right, so what I'm going to do is I'm going to clear this graph, and then I'm going to continue running the whole thing. So watch what happens. Looks pretty similar, right? Everybody agree? Is there any difference? I don't know if you can see. What does it say up here? Anyone see that? It's too hard to see. All right. It says times 10 to the minus 3. So that means this is not 2.5 anymore. It's 2.5 times 10 to the minus 3. It's much smaller. The same thing over here, it says 10 to the minus 3. So it keeps getting smaller and smaller. It looks just like the previous graph, but really, this thing here is a plot of what this was in the previous graph over here. It's just getting smaller and smaller. And you can see the time here continues to increase. It started at 50, not at 0. We could do this again. I clear the graph and then start it again. Stop it. This time, it's 10 to the minus 5 up there. I could keep going. It'll go to 10 to the minus 8, 10 to the minus 12. It gets smaller and smaller. So it approaches 0 exponentially. So we have an exponential approach to 0, and therefore, but it's still oscillating. All right, let's see if that always happens. Let's see if that behavior is always the case. So what do you think would happen if I made the damping coefficient, this gamma, bigger? What's going to happen to this curve, for instance? There's no oscillations? You say no oscillations. Well, let's try that. Let's see what happens. I'm going to double the damping. Do a new guy here. Make that 0.4. Initialize and start. So you notice anything? What's different? It's still oscillating, but what is different? What's different from what it was before? Decrease faster? How about the number of oscillations? See, it looks like there are fewer there. Of course, it'll still be more oscillations here, but smaller, right? We could try that. Let's clear this. Start again. And you see you get the same kind of behavior. All right, so the damping is faster. Let's make it even bigger, the damping. So we'll go do a new one here. I don't know, let's try 0.6, see what happens. We get even faster decay and fewer oscillations. So here's the question. Is there a point at which there are no oscillations whatsoever? None whatsoever. Let's see. Let's make it bigger. Let's go all the way to, let's say, 1. Let's go all the way to 1. Initialize, start it. All right, well, we still have one little oscillation there. So 1's not enough. All right, let's go to even bigger. Let's try 1.5. Initialize, start. Up. There we go. There might be a little oscillation right there, but maybe not. And if I went to 2, there it's pretty clear there's no oscillation. So we have two possibilities. We can see oscillations, or we have no oscillations. It decays exponentially. Mathematically, this is described in the following way. So the first case with oscillations, the solution turns out to be an exponential damping times a cosine function. That occurs when the frequency is bigger than this omega over 2. When omega 0 is bigger than the gamma over 2, the damping, by enough, you get oscillations. This is called under-damping. So this situation is called under-damping. The other possibility is the reverse, where omega 0 is less than that, and you get this solution. All right? And this is what's called over-damping. So it turns out there are two exponential solutions, and you add them together. And that's called over-damping. There are no oscillations in here. There's a third case that's almost impossible to reach, where this omega 0 is exactly equal to the damping over 2. That is called critical damping. And critical damping has a funny solution. It has an exponential solution plus time times the same exponential. All right. So what is the importance of this? Where do we see all these kinds of damping? Well, we see it in all kinds of electronic circuits. We see it in our body. We have oscillations that are damped. All right. What does the body do? So your heartbeat does not damp down to 0, does it? Hopefully not. It may do it when you're almost dead, right? Right? When you're dying, that's probably what happens. You have heartbeat oscillations, and then they go to 0. You know, you've seen those movies in the hospital where they show the oscillations, and then all of a sudden there's nothing. All right? That is that's damped oscillations. And that's when you die. All right? So something must keep you alive, right? And that's what we're going to talk about next, okay, is what keeps those oscillations going. All right? But before I do that, I want to talk just a little bit about where critical damping actually occurs. I actually wanted to test the door in the back. This door doesn't have any damping at all. But if you look in the back, those doors, here, let's take a look at them. There's a spring-like thing in the door. So if I let this door go, so I'm going to just let it go. All right, you see that? That spring is not adjusted correctly. It's underdamped. That's why the door slammed. Let's look at this door over here, see if this one's adjusted better. So I'm going to let it go. Now this one's interesting. So that went much slower. It had two stages, probably because there's like 2 springs in there. But a well-adjusted door should be adjusted to be a critical damping. That's how it should be adjusted. Why is that? Why do you want that? Because you don't want it to slam. That would be underdamping. And you don't want it to take forever to close. That would be super overdamping, right? You want it to be right at critical damping. All right? Now, when I was growing up, I had a door called a screen door. Anyone know what a screen door is? It's made out of a mesh screen. It's sort of the door outside the main door. And it had this kind of mechanism in it. And we would adjust the spring tension to get it so that it would not slam against the, against the door. So it wouldn't slam, or it wouldn't take forever to slow down. So that's an example where critical damping is used. You try to get right at critical damping. All right. So how does oscillations keep going? So for example, this is the old way in which radios worked. The oscillations in the electronic signal actually came from the air. You had a radio signal that was basically oscillating. It went into the antenna. The electrons in the antenna oscillated, and that's what kept some oscillation in the circuit going. So that oscillation kept going, and then the radio converted those electrical signals to sound. Now, the way modern radios and TVs work is a lot more complicated than that, so I don't even know how they do it. It's all digitized now. But in the old days, that's how it worked. There was basically a system that could be mathematically described by this formula here, and then we'd add in what's called a forcing term that depended on time, like that. Okay? So you have two omegas here. This omega 0 is what we call the natural frequency of the oscillator. And this is an external forcing frequency. All right? So let me give you an idea what that might look like in this pendulum. So here's a pendulum. And it'll slow down, like usually. But I can force it by doing this. And if I was good at it, I could keep it going. Okay? In other words, I'm adding energy to it. All right? Or another way of doing that is, maybe it's a little easier with this. All right? So this thing's going like this, but every once in a while I can hit it. And if I hit it at the right time, it'll actually have fairly high oscillations. How many of you have ever been on a swing? You know what a swing is? As a child, you've been on a swing, right? And you try to get going, and then your mother or your father pushes you, or a friend. All right? There are good ways of pushing you, and there are not so good ways of pushing you. If they push you every time you came back at the end, then they're pushing you at the right frequency. But if they're starting to move that way, and then you start pushing, or they're coming back and you don't push it the right, you won't have as good an effect. So how does that work? We now have this new equation that we have to solve. Here's the new equation. We put in this forcing term here, and then we end up with an equation that looks like this. Okay? Basically, I should write this over m. So this is A0. Okay? All right, so we have this forcing term that's added to the equation. What's the solution? The solution to this equation is the original solution before plus this equation called the steady state solution. Why is the original solution also still part there? Because if I take away this, I get 0. So if I put in this plus the original solution into this equation, the original solution will die off to 0 after a long enough time. So theta t, for instance, would equal, we could call it the transient solution, which is a function of t, plus the steady state. So if I stick this solution into here, the transient part goes to 0 because without this, we get 0. We just get 0 when we put it in. And this part, when we put in here, takes care of this term. All right? It's called a particular solution. And so you get this solution comes there. All right. And it has a certain amplitude. And the amplitude is given by that formula. Originally, I was going to ask you to try and show this, but it's just a lot of math, not much physics in it. Really, the only thing that's interesting is the solution. So it turns out this is the general solution. Notice when omega equals omega 0, we get the maximum steady state amplitude. That is called resonance, resonance, resonance. And the world works on resonance. We use it all the time. All right? So your heartbeat is at some resonant, is not at a resonant frequency, probably, because that would be, the oscillations of your heart would be too big. All right? But at some frequency, this will be a maximum. And usually, various devices are designed to be, depending, they might be designed to be very far from a resonance or to be very close, depending on whether they're using the oscillations. Notice that at the resonant frequency, so when omega equals omega, at the natural frequency, at the resonant frequency, when omega equals omega 0, we also, the phase angle goes to 0. All right? So that means the thing is right in phase all the time. Okay. So this is resonance. Most mechanical engineers, when they design, machines, or architects, if they have any mechanical background, when they design buildings, they want to avoid possible resonances. All right? Because, machines oscillate. Cars, they oscillate. If they happen to oscillate at a resonant frequency, they're going to oscillate some more. And that could cause damage to the machine or damage to the building. So it's very important to find the resonant frequencies in these devices. And once they find those resonant frequencies, they change the building or they change things so that you're far away from any possible oscillation. What could cause the oscillations? What's the forces that could cause it? Well, sometimes in a machine, the machine is like a washing machine. You've probably seen washing machines go into resonance. If you have a certain number of clothes in the washing machine that's not quite right, okay, it can cause the machine to vibrate a lot. Okay? So the machines are designed to avoid that. All right? Buildings are designed to avoid that as well. So that's what we call resonance. Now I'm going to tell you a story, my favorite story about resonant phenomena, because it happened to me. So I had a car, a Toyota Tercel, when I was actually about 30 years ago. And on top of this car, I had a luggage rack. Okay, so here's what it looked like. So I had a car. Here's my car. Some wheels. And it was sort of flat up here. And on top here, I had a luggage rack on top of the car. Okay? Here's me in the car. Okay? So I'm in the car. The luggage rack is empty. And what it's made of is like metal bars going around in a rectangular shape. So the luggage rack, if you're looking down this way, just look like a square, like that. So there were kind of like that, like that, like that, like that. So you're looking down, there are bars there, and you put the luggage in here. Okay, so this was in the car. And one day I'm driving. Usually we don't even have the luggage rack on the car, but we were going on a trip soon, so I put it on, but it was empty. And the luggage rack, so I started driving, and I heard this noise coming from the top of the car. And I drove faster, and it got worse. And then I said to myself, being a physicist, right? What is going on? Why is it making that noise? The luggage rack is clearly vibrating. And what's happening is air molecules are hitting this side, and then they go through, and then they hit that side. So there's a characteristic time between when it hits here and when it hits here. So it's like this forcing term here with a characteristic time, which means a particular frequency at which the air is forcing the luggage rack to oscillate. So I say to myself, aha, let me see if this is a resonance phenomenon. All right, so how would I do that? How would I test whether this equation is working, this one here? Well, if I'm right, if I go fast enough, then this frequency will go above the natural frequency, and the amplitude will start to go down. Right? So the intensity of noise should go up as I increase my speed, and then go through a maximum and come back down. I had no idea what speed I had to drive at. But I thought, let's try. Okay? So I go out to a deserted road, okay, because I'm going to try and go pretty fast. And I look around, make sure there are no police cars in the area, and I start driving. So I drive faster and faster. The noise gets worse and worse. And then I get up to about maybe 130, 140 kilometers per hour, pretty high, really fast. And sure enough, the noise just went away. It just went away as I went fast enough. And then when I slowed down, it came back. Sped up, went away. So that is clear evidence of resonant phenomena because I changed the frequency of the external force on the oscillator. And that's what did it. Okay. So that's my favorite example of resonance. You will see resonance, and we'll talk about it a little later when we talk about waves and standing waves. Resonant phenomena is really what's behind almost all musical instruments. It's all based on resonance. I think every solid has certain modes in it that are oscillatory modes, and if you hit one of them, I guess you could cause it to break. So there's vibrations in the glass. Actually, it's a glass, not a crystal, in the glass. And there's certain special frequencies. And if you happen to excite one of them by usually a very high-pitched frequency, then you will cause the oscillations to go big, and that could break the glass. Yeah. There's some controversy about that. There's a famous bridge called the Tacoma Narrows Bridge. Our textbook actually mentions it. They're a little bit slippery in what they say about it. The present thinking is that it's not really resonant phenomena. Yeah. That instead, it's a complicated phenomena that has to do with turbulence, which is a much complicated thing about fluid. So the idea that there's a particular resonant thing there, the thinking is it's not really true. Because the wind that came through was not really oscillating. And so it's a little bit of a stretch. This has been used in introductory physics courses for 50 years or so, in yours. Yeah, it's probably not really the main effect. Probably not. That's what I heard. I'm not a civil engineer who would have to look into it more carefully to see. That's a very dramatic video to look. It's called the Tacoma Narrows Bridge. But I don't think it's really a resonant phenomenon. To check it, what they would have to do is, which they couldn't do, obviously, would be to have like a hurricane go through with much higher wind speeds and see if nothing happened. All right? So that's one way you could check to see whether that's the case. These are the main ways in which this phenomena works. Now, I am going to backtrack a little bit, and I'm going to consider this equation here, but I'm not going to make this approximation. I'm not going to make the small angle approximation. And let's see what happens. So I'm going to take out the damping. And I'm going to zero. And I'm going to take out the forcing stuff. All right, so here's our regular old harmonic oscillator. Okay, so you get a nice, simple sine wave, and we get an ellipse in the angular velocity here. All right. So I am going to pick, let's pick a very large angle. So this is 0. That's 90 degrees, right? So that's pi over 2, let's say 1.6. All right, so I'm going to start this out, theta, at 1.6 instead of 0.4. And let's see what happens. That's a pretty large angle. That's, all right, so we initialize it, we start it, stop. Doesn't look that much different. If you look closely, this is a little more egg-shaped than elliptical. It's not quite elliptical. But it's amazing how good this approximation actually works. Even for relatively big angles, it's pretty good. But not good enough if you go to really large angles. So let's go all the way up to close to pi. So this would be if I started out like this, right? Something like this. All right, of course, there's a lot of damping there, but let's see what happens if there's no damping. All right, there you go. So here you see you get quite a, it's not really sinusoidal like before. I mean, that looks sinusoidal, but it's really not quite sinusoidal. And you also get, clearly this is not a pure ellipse. All right, this stuff up here has to do with the fact that when it's near the top, it actually stays there a little longer than usual. All right? I don't know, I can't really simulate it. This simulates it better. Okay, so this is what's called a nonlinear effect, right? Because sine of theta has terms in it, if you expand it out, would not just equal theta. Theta is linear. This is nonlinear. It's called nonlinear effect. And why do I bring this up? The world is nonlinear. Okay? It's not that linear in many ways. Unfortunately, most people, including most economists, spend their lives dealing with the economy as if it's linear. Now, I don't fault them because to do anything nonlinear is extremely hard. So that's why they do linear things. But it's also why they can't predict anything. All right? Why are economic predictions so poor? It's because it's very hard to know what's going to happen in a nonlinear system. And I'm going to show you a dramatic example of that in a few minutes. All right. So this is the nonlinear situation here. Now what I'm going to do is I'll add damping, and we'll see what happens. Nothing too surprising. So I'll just add a little bit of damping. All right, initialize it, and then we can start it up. All right, so more or less does the same kind of thing as before. Not too surprising. Not too surprising because for large angles, the motion still looks close to sinusoidal, even though it's not exact. But now what I'm going to do is I'm going to add forcing to the system. I'm going to have an external forcing term. It's a little different than what I have up here. So let me write it down. So I'm going to write down the equation I'm going to use. The reason I'm using this is because me and many other people have analyzed this equation a lot. So the equation we're going to look at is this. So what you're going to see is a simulation. It looks similar to what we had, but a little different. All right, so that's the situation. What we're looking at is a situation where omega 0 is set equal to 1 here. Oops, I have to write down here. All right, so that's it. Okay, so without this term here, we have what we had before, sine of theta. And so omega 0 is 1, because I just have a 1 here. And our frequency, omega, is 2. Okay, so that's the driving frequency, the external frequency. Now we know omega times the period is 2 pi. So if I put in 2 for this, I get that the period is pi. All right, and the reason why I mention that is because that's what's behind this point, this map here. We plot things every pi seconds because that's the frequency of the driver of the, that's the period rather, of the driving frequency in this system. All right, now let's see what happens. We'll keep our damping. I'm going to put in just a small amplitude of this driver thing here. And I start it out kind of small, so it just dies out pretty much. There's probably very small, whoops, I didn't put it in right. So let me, that's wrong. It doesn't, I don't even know what it read in for that with 2 decimal places there. 0.2. Did I do that right? All right, now let's do it. Ah, that's a little better. Yeah, that's what I expect to see. So you see there are small oscillations. This is the steady state behavior, and this part is the transient behavior, this part in the beginning. So this part here is this transient behavior, and after a long time, this stuff has gone to 0, the transient stuff, and we're left with just steady state oscillation. So we can look to see if there's some kind of resonance, but I'm not doing that. Here, I'm not changing the frequency. The frequency is always the same. The only thing I'm going to change is this amplitude. All right? And we're going to see some really interesting things happen. All right? So let's increase the amplitude and just do it systematically so we can see what's happening. All right? So now it's up to 0.4. And I get that. All right? So the oscillations get bigger and bigger. And I could clear this off. And we can see what the steady state behavior looks like. Pretty much like that. OK? So this funny kind of shift is due to the fact that I'm using, this is multiplying sine theta rather than being separate. All right. Still not too exciting. And I like excitement, so let's keep going. See if we can get anything new out of this. All right, that's still pretty much the same. Maybe a little bit of something going on there. Let's clear it, see if anything new is happening. Nope, still pretty much the same. OK, so it's still oscillating. All right, now I'm going to keep going. Let's see, that was 0.6. Let me go to 0.8. See what happens there. Initialize, start. Uh-oh. Let me clear that, see what's going on here. Huh. What's going on? What is going on? What is the pendulum doing? Here's my pendulum. All I'm doing is this. That's all I'm doing. That's what I'm doing. So what is happening here? Do you notice anything? So here's the angular frequency versus theta. So theta goes from -3 to 3. What about the angular frequency? Let me do it again, clear it again, and just do it. I just stopped it. So what does this mean? What's going on there? Yeah. What do you think's going on with this pendulum? Remember, there's only theta. Theta goes from 0 to 2 pi, so, or from pi to minus pi. So here's minus pi, roughly. Here's pi. Right? You can't go any other way. So this is pi. That's pi. That's also minus pi. And that's 0. Ah. So somebody knows what's going on. What's going on? Yes. Everybody, take your finger and do this. Right? This is what's going on. The pendulum is doing this. It's going around and around and around. How do you know that from this? Yeah. Well, it's connected at the two sides, but also notice the angular velocity is always negative. So it's always going in one direction. If it oscillates like this, the angular velocity changes from positive to negative. But if it's going around and around and around and around like that, it's always the same sign. Now, whether it's negative or positive, I can't predict in advance. Also notice it kind of repeats itself after 2 pi. So here's where the Poincaré map is useful. Notice there's only 2 dots on the Poincaré map. All right, so we say that we have a period 2, we say, because we have 2 of these guys here. Okay? All right, I could get a period 1, I think, if I go to a little smaller. Let me do that. Let's go down to about 7.7. Let's see if I get period 1 there. Let's clear it. Clear it. Yep, there we go. Clear, start. All right, so now I have period 1. Pretty much, yeah. So that's a period 1. All right. So I got period 1. I got period 2. What do you think the next period is? So you might think 3, right? So let's see if we can get a period 3 out of this. It was 0.8 before. Let's try 0.85. See what happens. All right, so that's that. Let's stop that, clear it, start it again. Well, that still looks like period 2, right? There's still 2 dots. So let's keep going. What do you want to try? You want to try 1? Let's go a little slower. Initialize. No. Oops. Initialize. Start. So that's 0.87. All right. I have to wait for the transient behavior to go away. It's still 2 at 0.87. All right. Let's go to 0.89, see if we get anything different. I forget where the interesting stuff starts. All right. All right, so this is all transient behavior, this complicated thing up here. I want to look at the steady state behavior. That still looks like period 2. All right. Let's go further. Let's go all the way to 1. Somebody wanted to go to 1. All right, I'll do that. Even though I know that's not good. But all right, maybe it'll work initially. All right. Clear it. Let's start up again. Ah. There we go. We have period 4. So we had 2 before, 4. So maybe between 0.9 and 1, it's period 3. So let's keep trying. Yeah, I'm a scientist, so I don't want to discount your ideas there. So let's try 0.95, right? See what that does. All right, there's the transient behavior. Let's clear it. All right, so 0.95, we're still at 2. At 1, we were at 4, right? So let's do 0.98. Initialize. Let's start. All right, stop. Let's clear that. Start. It still looks like 2. I guess I'll do 0.99. Let's see what happens. It's hard to see. Let's see. Up. So there it's back up 4. There's 2 here, and this probably is very close to 2. So somewhere around 0.99, the period is 4. So we had period 1, period 2, period 4. What do you think the next period is? 8. All right. Let's see if we can get 8. 8's kind of hard to do. Let's see, 1 was, let's do 1.1. Let's see what that does. All righty. Lots of transient behavior. Whoa, this thing's going crazy. Let's see. I don't think this is going to settle down to anything nice. All right? So I think we're going to have to go a little bit lower. Let's go to 1.01. See what that does. That looks promising. So I still have 4, right? All right, so 1.01, let's try 1.02. 1.1 was too much, right? That seems to stop. Let's see what we got here. It's still around 1, 2, 3, 4. Yeah, still 4. Let's see what 1.03 does. Oh, that's kind of problematic. So let's try 1.025. Oops. What was it? 1.025. Okay. Something might be happening there. Let's clear that. Well, could be 8. These are thickening up a bit, so it could be. Let's clear it and see. We're very close to 8 here, because that's there. Okay. So anyway, what happens here is it goes from period 1, period 2, period 4, period 8, period 16, 32, and the change in the amplitude needed gets smaller and smaller to get to those different what are called period doublings. And then at a certain point, a critical point, which is around 1.02 something, the thing will not have any period at all. It'll be totally chaotic. Totally chaotic. And this is called the period doubling route to chaos. Okay? All right? And it's well known. It was discovered about 30, 40 years, maybe 40 years ago. A guy named Mitch Feigenbaum at Los Alamos in the United States actually first discovered this period doubling route and quantified it, how it went. It turns out that it's universal behavior. All systems that go through a period doubling route to chaos do it in the same way. All right? And why is this relevant? Well, your heart and your brain, despite, well, maybe you realize this, is chaotic. You want to be near, very close, if not over, the place where the brain is chaotic. Why? You want to be near that. The reason is that that gives you more flexibility to adjust to environmental changes. All right? So if you are, maybe you know about people who have seizures, epileptic seizures. Okay? The problem with seizures is it's not chaotic. The person has a very regular oscillating brainwave, and that's not good. So you don't want that. You want to have a chaotic brainwave, and you want to have a chaotic heartbeat. All right? It's more or less oscillating, but there's got to be some chaos in it. Otherwise, your body can't respond to environmental influences fast enough. All right? So here's the lesson for you. Live a chaotic life. Okay? Because if you live a chaotic life, then you can adapt to things much better than if you do the same thing over